Welcome to Late Night Chemistry with Mr. Harden. Today's episode, Limiting Reactant Problems with Quick Stoichiometry. Limiting reactant problems are problems where you know more from the amounts of more than one reactant. The difficulty is you have to figure out which one of the ones is the limiting reactant. The other reactant, the excess one, you cannot really use for calculation because not all of that material is reacting. Only the limiting reactants, all of its material is reacting along with a certain amount of the excess reactant as well. So in these problems, it is vital first to figure out the limiting reactant because that will be what we use to determine all of the other calculations. Now, using quick stoichiometry, there's a quick way of doing these problems. First, a little mini review. Here's our quick stoichiometry plan. You can start with either grams or moles of one particular substance. You start with grams. To simplify it, you can divide by the molar mass to make it moles. From there, you can go from moles to as simple as possible, which would be mole equivalents. We'll just call it equivalents for short, just by dividing by the coefficient you'd find in the balanced chemical reaction. Once you're down to mole equivalents, everything else is uphill from there. It's all multiplication. So if you multiply the equivalents by the coefficient, you get the moles. And then if you multiply the moles times the molar mass, you get the grams of whatever substance you have to be looking for. Okay. In this process, A is not necessarily a reactant and B is not necessarily a product because you can start anywhere in this chemical reaction and go anywhere else. Now, in a limiting reactant problem, you're given the information on two different reactants, specific amounts. So you're definitely going to be starting with a reactant in one of these problems. But you have two reactants that you need to deal with. So the method that we're going to look at is on our next page. For our first reactant, we'll call it reactant A. We're just going to follow the first parts of our quick stoichiometry plan. We'll convert it down to equivalents. Again, grams divided by molar mass give moles. Moles divided by the coefficient to give equivalents. For our second reactant, let's call it reactant B, we're going to do the same thing. We're going to, regardless of where we start, whether in grams or moles, we're going to convert to equivalents. So grams mole divided by the molar mass, moles to equivalents divide by the coefficient. Now, once you're at equivalents for both of your reactants, well, then your life is simple enough. The smallest number of equivalents comes from the limiting reactant. So whichever reactant gives you the smallest number for equivalents is your limiting reactant. The other reactant is an excess reactant. All the calculations are to be done for your limiting reactant. And here's the real beauty of this. You've already got the limiting reactant down to equivalents. So all you're left is that last leg of quick stoichiometry, the multiplying side of things. So for the rest of the problem, it will be just involving taking the equivalents from smallest number of equivalents and multiplying until you get to the answer you're looking for. Let's put that to use in some examples. Example 1. In this reaction of Fe3O4, which is a type of iron ore, with aluminum to make iron metal and aluminum oxide, 300 grams of the iron ore is reacted with 800 grams of aluminum. Determine the mass of iron that will be formed in this process. So this is a classic limiting reactant problem because you know about how many grams you have of the iron ore and the grams of aluminum. And our first step is to figure out which one of those two reactants is our limiting reactant. Our plan for our solution is one, determine the limiting reactant, and then we'll use a limiting reactant to calculate the mass of iron, and that is the equivalence from the limiting reactant we use to calculate that mass. So let's look at our steps. So in our first step, we'll take our first reactant, the iron ore, and we will convert that into equivalence by first dividing by its molar mass of 231.55 grams per mole. And again, you can obtain that by adding up 3 irons, that's 3 times 55.85, plus 4 oxygen, 4 times 16 to give you 231.55. Once you've got it to moles, you can then divide by the coefficient in reaction. So in the reaction, what's in front of the iron ore, there's a 3, so you divide by 3 to give the number of equivalents. So 0.432 equivalents. We do the same thing for aluminum. 800 grams of aluminum divided by its molar mass of 26.98 grams per mole, and then dividing by the coefficient in front of aluminum, which is the 8. It says 9 here, but it's supposed to be 8. That is a little, well, I could call it a typo, but it's more of a write-out. To give you a number. Now that number, I'm just double checking it real quickly. It's really supposed to be 3.71 equivalent. But here's the thing. It's not going to really matter so much because you only have 0.432 equivalents of the iron ore. The much smaller amount of iron ore is telling you that the iron ore is a limiting reactant. So you're going to run out of the iron ore a long time before you run out of the aluminum. So our iron ore is limiting reactant. Aluminum would then be the excess reactant. And then we will complete the problem, which is to calculate the amount of iron, and that calculation comes from the limiting reactant. So if you take the equivalence from the limiting reactant to figure out grams of iron, you just multiply times the coefficient. This is where it is supposed to be 9, because there's a 9 in front of the iron. So 0.432 equivalents times 9, that will give you the moles of iron, times 55.85 grams, that's the grams mass for each mole of iron, to give you 217 grams of iron. Example number 2. The reaction of aluminum with sulfur is depicted at the top. You might remember sulfur is octatomic, so this reason is represented as S8. But we're just doing a simple synthesis reaction here. Question is, 260 grams of aluminum reacts with 300 grams of S8. And here I've divided up the different steps of the problem. I'm asking to determine the limiting reactant, determine the mass of the aluminum sulfide that's formed, and then I'm adding the extra question. And that is determining the mass of the excess reactant that's left over at the end of the reaction. Yes, I know it's kind of worded vaguely, but that's so as not to give away the identity of the excess reactant from the start. So, a little pause so that you can see what you could do with working on your own, and then we will work it all together. Okay, for the A part, take 260 grams of aluminum, divide by its molar mass, 26.98. That would give you moles, which if you then divide by its coefficient of 16, you'd end up with equivalents. That should be 0.602 equivalents of aluminum. Likewise, you do the same thing for sulfur. 300 grams of sulfur divided by 256.48 grams of sulfur per mole. Okay, that's because there's S8 has 8 sulfurs in it, so 8 times 32.06. Divided by its coefficient of 3 to get you 0.390 equivalents. That is the limiting reactant. Notice the limiting reactant is not necessarily the one that has the least number of moles or the least mass. It's the one that has the least number of equivalents. Aluminum would then be just your excess reactant. B part. We're using our limiting reactant. That's equivalence from our limiting reactant. That's what we're going to use for the basis for all of other calculations. So 0.39 equivalents, you multiply it times 8, which is the coefficient in front of aluminum sulfide. Times the molar mass of aluminum sulfide gives you 468 grams of aluminum sulfide. Now the C part was determine the mass of excess reactant that's left over at the end of the reaction. So we already know how much we had to begin with, 260 grams of aluminum. Of that 260 grams, we have to figure out how much is actually reacting. Well, we can calculate that using our limiting reactant. So if we take our limiting reactant, 0.390 equivalents, there are 16 moles of aluminum for every equivalent. Then there are 26.98 grams of aluminum for every mole. So if you multiply that out together, that's 168 grams of aluminum that's used in this reaction. Now, you start with 260 grams, you use 168 grams up, which means at the end there's 92 grams of aluminum left over. So to figure out how much of the excess reactant is left over, you calculate how much you actually used, and you subtract that from how much you have at the start. In our last example, ammonia is reacting with iodine to make nitrogen triiodide, as well as making hydrogen gas. This is definitely a reaction I would not recommend doing at home, as hydrogen gas is highly flammable, and of the two products, it's the least hazardous of the two products. Nitrogen triiodide is a highly sensitive explosive. At the slightest disturbance will explode. Now, the question is, if you start off with 5 moles of ammonia and you react with 6 moles of iodine, what mass of nitrogen triiodide could be formed? So, my suggestion, pause playing this video right now, work out the problem, following the plans we've talked about, and then see how your solution compares to my solution. Hopefully you just finished working through the problem And let's see how it compares. So in my solution, since we already start off with moles, it's one step from there to figure out equivalence. So the 5 moles of ammonia, we divide by its coefficient of 2, we'll end up with 2.5 equivalents. We're going to do the same thing with the iodine. We got 6 moles of iodine divided by its coefficient of 3 to give you 2 equivalents. Well, 2 equivalents is going to be our limiting reactant. So iodine's limiting reactant. And we used 2 equivalents to figure out how much nitrogen triiodide is formed. So 2 equivalents, multiply times the coefficient for nitrogen triiodide, which is 2, and then by its molar mass, which is 394.71, you'd end up with 1,600 grams of nitrogen triiodide. Now, hopefully today you should be able to do stoichiometry problems involving limiting reactants. And quick stoichiometry does make this process a whole lot easier to do. Good luck. Bye.